Okay, in this video we're going to continue our discussion of multiplying polynomials. We're going to go into a couple of special cases. And keep in mind, we're not changing any rules. We're still just going to distribute these polynomials the same way that we did in the last video. This time we're just getting into a couple of special cases. Okay, first example. Let's multiply out a perfect square binomial. What that means is a binomial, two terms, we'll just make one up, say it's x plus 2. Perfect square means we're going to square it. Now it's really tempting when looking at something like this to just square the x and square the 2 and get something like this. Unfortunately, that is not the case. That's highly illegal, gets a frowny face. It's actually probably the most common algebra mistake that I see as a teacher. So make your teacher happy and don't make that mistake. The way to do this correctly is to actually multiply out the binomial by foiling. I call it foiling, you might call it distributing. However you do this, we're going to multiply the first two terms together. That's x times x is x squared. We're going to multiply the outer two terms together. That's x times 2, that's 2x. The inner two terms give us another 2x. And the last two terms give us 2 times 2, which is 4. Of course, now we can combine like term. 2x plus 2x is 4x. So we get x squared plus 4x plus 4. Okay, let's look at difference of squares binomials now. Multiplying difference of squares binomials looks something like this. Here you have the same two terms in your binomial, except in one you're adding the two terms, and in the other you're subtracting the two terms. Let's see what happens. Again, we have to FOIL this out. Multiply the first two terms. X times x is x squared. Multiplying the outer two terms is 2 times x. Multiplying the inner two terms now is negative 2 times x. So that's going to be a negative or a minus 2x. And multiplying the last two terms is negative 2 times positive 2, which is negative 4. Now you'll see what happens with the like terms here, and this is always the case with these difference of squares binomials. The two like terms in the middle here actually cancel each other out. Plus 2 and minus 2 cancel. And the only thing we're left with is an x squared minus 4. This is actually why this is called a difference of squares binomial. What we're left with is the difference, the subtraction of two perfect squares. You have x squared and 4. We're going to talk a lot more about difference of squares when we get to factoring. Now what mathematicians like to do a lot is come up with formulas for these types of things. Let's come up with a formula for this difference of squares situation. So let's say we just had a minus b times a plus b. A now can represent anything, any number or variable or combination, and b can represent anything as well. If we multiply these things out, we have a times a is a squared. The outer two terms give us a times b, so it's plus a times b. The inner two terms are negative b times a, so that's going to be a minus a times b, or b times a, it's the same thing. And the last two terms, minus b times b, is going to be a negative or minus b squared. Again, the middle two terms are going to cancel each other out, and we're just left with a squared minus b squared. If we box that thing up, that is the general formula, general equation for multiplying difference of squares binomials. And you're going to see this again when we talk about factoring. I tell you what, I'll give you the formula for perfect square binomials. There it is, that's the formula for perfect square binomials. See if you can come up with that, where that equation came from. For now, let's move on to multiplying polynomials that have several variables in them. Let's multiply out these two binomials, xy minus 3z times x plus y squared. Now the rules don't change just because we have a lot of crazy symbols going on here. We still have to just FOIL or distribute. Multiply the first two terms together and you get xy times x. Multiply the outer two terms together and you get xy times y squared. Multiply the inner two terms and you get negative 3z times x, and you multiply the last two terms and you get negative 3z times y squared. Now we have a couple places here, a couple of terms where you have similar bases multiplied by each other, so we can combine those using the rules of exponents. X times x is just going to be x squared. So we have x squared times y. In the next term, we can just carry down the x, and we have y times y squared. Y times y squared is y cubed. On the other terms, we can't really combine anything, but you can get rid of the times sign. So you have 3, I'll say xz to put things in alphabetical order, and we'll say 3y squared z. Now what we have is a polynomial with 4 terms, and there are 3 variables in this thing. We have x, y, and z are all variables in this polynomial. One question you want to ask yourself is, do you have any like terms? And in order to have like terms, we have to have all the same variables with the same powers. In this case, we don't have any of the same variables with the same powers in combination in any of these 4 terms. So we can't combine any of these 4 terms, and that's our final answer. Hopefully you're asking, when can we combine like terms when we have a polynomial with several variables? The answer is you have to have all the same variables with all the same exponents. So here we have 2 terms that have the same variables, x and y. However, we have an x squared y here, and we have an xy squared in the second term. So we can't combine those 2. But there are 2 terms that we can combine, 3x squared y and 5x squared y. We can combine into an 8x squared y. We just added 3 plus 5. The other 2 terms are not like terms, so we can't combine them in any way. We just copy it down, 4xy squared plus 6x squared z. So in this example, we combined our like terms and ended up with the polynomial below. Alright, for your video quiz, do the following multiplication problems. Good luck, and I'll see you in class.